Okay, everyone, so this is the last practice problem I'm going to do with you. This is the first problem from the worksheet that I posted on that Google Classroom assignment. So if you get out the piece of paper you plan to use for that assignment and you have your calculator ready, then you can follow along with me and you're guaranteed to get at least one of these problems right. So we're looking at mice in the Sonoran Desert, and they have two phenotypes, dark or light. Dark is actually dominant to light. And this is a good reminder that the word dominant just means it only needs one dominant allele for that trait to show up. So you could be one of these 6 dark mice, and that's your phenotype, but your genotype could either be homozygous dominant or your genotype could be heterozygous, and you could still end up being a dark mouse. Now, all that the word recessive means is that in order to be a light mouse, you have to have 2 lowercase letters. You have to be homozygous recessive. So remember, the whole purpose of doing these Hardy-Weinberg problems is that we know each one of those light gray mice is little d, so we know what their frequency of that allele is in the population. But all of the dark mice, we actually don't know which ones are homozygous dominant and are heterozygous. If we want to figure out which of those dark mice are homozygous dominant versus which ones are heterozygous, we have to do the Hardy-Weinberg equation. So that's what this whole exercise is about, is calculating these allele frequencies if all you can see is phenotypes, which is, realistic of a population. If you're a scientist, you're going to see gray mice and dark mice. You're not going to see homozygous dominant and heterozygous genotypes. You don't see those, you calculate those. All right, so we're gonna move up just a little bit so that we can do some math here. And A is asking us to calculate the frequency of individuals that display the recessive trait, little d. Sorry about that. So the little d genotype, homozygous recessive, is actually Q squared. Remember, I reminded you that Q squared is the value that we are always trying to find first. And it's always going to be a decimal point. That's what a frequency is. Well, right now we have mice. We don't have decimal point numbers. So we have to calculate how many recessive individuals there are. We have to calculate Q squared. Remember, Q squared is how many individuals have 2 lowercase letters. Well, if you count how many individuals in this population have 2 lowercase letters, they're all the gray ones. There's actually 15 gray mice in this population. You can count them if you don't believe me. Now, the total population size of these mice is 21. So if we want to calculate the frequency or the decimal point value for Q squared, we have to do the number of gray mice divided by the number of mice in total. So when we do that, we end up with 15 divided by 21, which when you plug that into your calculator, and you should all be doing that, you get 0.714. You can round this as much or as little as you want. The more you keep the numbers, the more accurate your results will be. So that's my Q squared value. I am done with A. So since I am done answering one part of the problem that it asked me for, I'm going to put a box around it saying, okay, I'm done with A. That way I get credit when I turn this in. Okay, now B. B is saying the frequency of recessive alleles in the population. This is your Q value. So B is asking us to solve for Q, not Q squared. It's asking us to solve for Q. So if it's asking us to solve for Q, we already know Q squared. You guys should know by now that all you have to do is the square root of Q squared in order to get Q. So I'm just going to do the square root of 0.714 in my calculator. And all of you should also be doing this right now with me. And I'm having some calculator technical difficulties, so work with me here. So square root of 0.714, and the number I get is 0.84, and I'm going to round that to a 5. So my Q value is 0.845. Since that's what this was asking me for, I'm going to put a box around it showing that I'm done answering that question. Now C is asking for the frequency of the dominant allele. So how many capital D's are there in this population? It's asking us to solve for P. Now remember, we're doing this in the order that you should always do this. You solve for q squared first, then you get q, then you get p. Now remember, we get p because p plus q equals 1. That's one of those equations that I taught you. And so we know that p is actually 1 minus q. So p, if we do 1 minus 0.845, which was the q value we calculated before, and you should be subtracting this in your calculator right now. So 1 minus 0.845 equals 0.155. Now that is p, that is what C is asking us for, so I can put a box around it. Now we have just D and E left to do. Now D is asking us for the percent of individuals that are homozygous dominant. Now remember, the individuals that are homozygous dominant, those individuals that are big D, their variable in the Hardy-Weinberg equation is just p squared. So all we have to do is just take the p that we calculated, so that would be our 0.155, and we just have to square that. Remember, if you have a simple calculator like me, I'm just going to multiply 0.155 times itself. And when I square this value, 0.155 times 0.155, I end up with a p-value of 0.024. Now that's not what the question was asking for. The question's asking for the percent of individuals in the population. So I have to multiply this by 100 because that's how you find percentages. So when you multiply that times 100, you end up finding out that 2.4% of the population is homozygous dominant. Now, E is asking us to find the percentage of individuals that are heterozygous. So remember, we're just finding out how many individuals have the variable 2pq. All you do now is multiply 2 times p, which we know is 0.155, times q, which is 0.845. And I'm going to have to start erasing some stuff soon, so sorry about that. Let's see what I can do here. Oh, I can actually just move that up a little bit. So I'm going to finish E up top here, actually. So I'll erase that down here. So for this one here, if we're solving an E for the number of heterozygous individuals, remember those are how many of our dark mice are big D, little d, then we're going to solve for 2pq. And so that means we do 2, once again, times p, which is 0.155, times q, which is 0.845. And I want you all to plug this into your calculator right now so you can find out that we have 2 times 0.155 times 0.845. And we end up with a 2pq value of 0.26. Now, that's still not what it's asking for. E is asking for the percentage of the population. So if it asks for a percentage and not a frequency, you literally just move the decimal place over. Or you multiply by 100. Either way, we know that 26% of our population is heterozygous for this trait. So that's how you do the math. Now remember, F is asking you to suggest a reason why that allele exists in the population. Think back to natural selection here. Why might there be more lowercase alleles or recessive alleles in the population than dominant alleles? Maybe it has something to do with the way that the environment looks, selecting for a certain color over another. So, couple reminders from here on out. Every time it asks you to answer a certain thing, like what's the percentage or what's the frequency or what's the amount or whatever, please make sure whatever it's asking for, you circle your final answer so that I know what you're looking for and I know what you found. Make sure that you show every bit of your work on the paper that you submit to me. I will be posting a key because I want you guys to get these answers right and I want you to know that you're getting them right. But I do not want to see on your piece of paper that you turn in that you have literally just copied down the answers and that's it. I'm not going to write down the work that I have done to get to that key. You're still going to have to show me all of your work. And most importantly, if you have any questions at all, please make sure you let me know so I can help you out as soon as possible. One final reminder, remember when we're doing these problems, it's just showing us the allele frequencies at one time. It's showing us the allele frequencies in that population of mice right there. If we want to calculate, or if we want to find out if evolution is happening or if the population stays at equilibrium, we need to calculate the Hardy-Weinberg equilibrium for multiple generations. So I wouldn't ask you to do that on the test. On the test, I literally just want to see if you can figure out how to solve this like once. And this is a really important AP biology skill, which is why I'm teaching it to you now. I want to introduce it to you so that you're more confident when you get to AP biology. It is a tough concept. I understand that, and I understand that this is not ideal conditions to learn it, but you guys are doing really great. I'm really proud of all of you. Keep up the good work. Try your best. That's all I ask of you, and I look forward to seeing your practice problems turned in by next Monday.